What we're going to look at is how we determine our Lewis structure. Now, our Lewis structure is a representation of how the atoms in a molecule are joined together. And they show us which atoms are bonded to which and gives us a little bit of an idea of the arrangement of the molecule. Now, in a Lewis structure, our electrons for each of the atoms is defined as either a bonding pair electrons or a lone pair, because they come in groups of two. Bonding pair electrons are found between two atoms, and they hold those two atoms together, and we'll depict them with a line. And then lone pair electrons, they belong to one atom, and we'll depict them with two dots. Now, when we are going to do our Lewis structure, we have a number of steps. The first thing we have to do is determine how many electrons we have available. And this is dependent on the number of valence electrons that all the atoms have. And we remember we can get the valence number from their group. And then we'll add one electron for each negative charge and subtract one electron for each positive charge. And then the least electronegative atom, or the one with the highest bonding capacity, will go in the center, and all the other atoms will be placed around it. We'll place single bonds between each of them, removing two electrons, and then we'll add our lone pairs, and then we'll add any extra electrons on the central atom as lone pairs. And if it has if there's no octet for the central atom, then we'll move a lone pair from the peripheral, and we'll go through this. And if it's a polyatomic ion, then we put it in a bracket. So one of the ways that I'm going to suggest that we do this, that will simplify it, is if we do use a chart to help keep track of what we have to do, for at least the beginning of it. And in the chart, we would list our elements. We'd look at how many valence electrons they each have, and we'll look at the total numbers, and we'll call that our have. We'll look at how many would be present in the valence energy level if it was required for each of them, and we'll call that our required. Then we can use those two values to determine our number of bonds and our number of lone pair electrons. So the first thing we would do is we would list the elements and state how many electrons are in each of their valence energy levels. So oxygen, being in group 16, has 6 valence electrons. So it has 6. And fluorine, being in group 17, has 7 valence electrons, and there's 2 fluorines that each have 7. So as a result, this gives us a grand total of 20. Now, if they were both to fill their valence energy level, then oxygen would have 8 in its valence energy level, and each of the fluorines would also have 8. So as a result, we require 24 to fill the valence energy level of each of our atoms, but we only have 20. So that means that they're going to have to form a number of bonds. The way that we're going to determine our number of bonds is our required minus our have divided by 2. And the reason we'll divide it by 2 is because each bond requires 2 electrons. So for example, I have 24 here, or sorry, I require 24, I have 20, so 24 minus 20 is 4, divided by 2 is 2. So that tells me that between oxygen and the 2 fluorines in this molecule, there will be 2 bonds. Now, the way that I determine the number of electrons in that are lone pairs, it would be my have minus my number of bonds times 2. This is because each bond has 2 electrons. So I have 20 electrons, and I have 2 bonds, so that means 4 of my 20 are going to be used up in bonds, which leaves me with 16 lone pairs. So because oxygen has a higher bonding capacity, it is our central atom. We know that we have 2 bonds and 16 of our electrons are in lone pairs. So I just wrote it down like this so that I can keep track of what I'm doing. So my next step is, as we stated above, we write our atoms with the central atom in the middle. So I have my oxygen in the middle, and then I have my 2 fluorines on the peripheral. Then I'm going to add a single bond for between each of them. So now that I've used up my 2 bonds, I have none left. Now I have 16 lone pairs to place, so the first thing I'm going to do is place them around the peripheral to give each of the fluorine atoms an octet. So this fluorine has 2 right now, so it requires 6 more. This fluorine has 2 right now, it requires 6 more as well. So I place the 6 around each of them. So that means now I've used up 2, 4, 6, 8, 10, 12 of my 16 lone pair. So I still have 4 electrons that go in lone pairs to place. My central atom is lacking an octet, so therefore it would go in the central atom. So this would be my Lewis structure for OF2, or oxygen difluoride. Now, one of the things we have to keep in mind is that some atoms will have what we call a compressed octet, and some will have an expanded octet. Okay, and a compressed octet means that they require less than 8 to fill their valence energy level when they're the central atom. And the 2 atoms that we will be looking at that might have a compressed octet are beryllium and boron. And if beryllium has a compressed octet, it only requires 4, and if boron has a compressed octet, it only requires 6. When we're looking at an expanded octet, where they require more than 8, the ones that we'll be looking at are phosphorus, which requires 10, and sulfur, which requires 12. And we can talk about this more in class. Like we did before with the previous example, the first thing we'll do is we'll use our chart just for a quick accounting so we know how many electrons we have and we have an idea of what's going on. And so boron, being in group 13, has 3 valence electrons. Oxygen, being in group 16, has 6, but there's 3 of them. So that gives me a total of 21. And then because this is a polyatomic ion with a charge of -3, I'm going to add 3 electrons, which means that I actually have 24 available. Now I can look at my required. Because boron is a compressed octet, it's only going to require 6 around it, rather than 8. And then each of my oxygens require 8. So that means that for this polyatomic ion, I require 30 valence electrons. So now we can figure out our number of bonds, which is required, minus our half divided by 2, which tells us 3. And then we can determine that our number of lone pairs, where I have 24, and 3 times 2, which is 6. So 6 of my 24 electrons are in bonds. That leaves me 18 to be lone pairs. So again, we're just going to summarize. Now boron has a higher bonding capacity than oxygen. Oxygen can only form 2 bonds. Boron can form 3. So therefore boron is my central atom. I have 3 bonds and 18 lone pairs. So the first thing I'll do, like we stated in the instructions above, I write my central atom with my peripheral atoms around it. I'm going to join them each with my lone pairs, or bonds, sorry, single bonds. There are now my 3 bonds. If I had a 4th bond, then I would write a double bond between one of the oxygens and borons, but I don't. Next, what I'll do is I add my lone pairs around my peripheral atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18. So in this case, I've used them all up. So I have no more lone pairs to place. I've placed my bonds, all my atoms. We always have to double check peripheral atom. Does it have its valence energy level full? And because boron has a compressed octet and it only requires 6, it's full. So therefore boron is satisfied. So I don't need to have one of these lone pairs come down and be a double bond. Finally, because this is a polyatomic ion, we would put it in square brackets and we would put the charge on that polyatomic ion as a superscript outside the bracket.